So this unit is all about bonding and nomenclature. Before we talk about bonding, let's go ahead and review some things we covered back in Unit 1. First and foremost, compounds are represented by chemical formulas, and these chemical formulas are basically the ratio of atoms in the compound. And when we talk about the compounds, we usually list the most metallic element first. So for example, if we were to take aluminum chloride, aluminum is more metallic than chlorine, so it's first. Then if we look at nitrogen dioxide, nitrogen is the most metallic between nitrogen and oxygen, so it's written first. And finally, magnesium chloride, because magnesium is a metal and chlorine is a non-metal. We also covered back in Unit 1 percent composition. It is the relative amount of each element present in a compound. And you would take the molar mass of the compound, and you would take the mass of each element and divide it by the molar mass of the compound times 100%. And that's what this equation right here indicates. So for example, if we were to look at the sulfate ion, it's 1 sulfur and 4 oxygen. So if I were to take the molar mass, I would have to take 1 sulfur, which is 32 grams, and add 4 oxygens, which is 4 times 16 grams per mole. And that would give you 96 grams per mole. But I'm looking for sulfur. So since there's 1 sulfur, I know the mass of 1 sulfur is 32 grams. I would take that 32 grams and divide it by the total mass times 100, which means it has 33.3% sulfur in a sulfate ion. So empirical formula is the lowest whole number ratio. So basically it is the simplest ratio for a chemical compound. And so let's go ahead and take this pie chart into consideration. If we look at this pie chart, it is divided into 18 different pieces or slices. And 6 slices have been highlighted. If I were to go ahead and simplify this, I can go ahead and combine each 6 slices over here, and I'd end up having 1/3 of a pie being completely removed. So I would have just did this 6 over 18 and divide both the top and the bottom by 6 and get 1/3. Similarly, we can go ahead and apply that to chemical formulas. So for example, if we had a chemical formula of C2H4, I can divide both of these by 2 and I'd end up with CH2. Now with molecular formula, this is the actual chemical formula of a compound. Empirical formula is the smallest ratio, while molecular formula is the actual. And remember, back in the day, we even said that an empirical formula can be the same as your molecular formula. But how do you determine the molecular formula? It's basically given to you by this equation. Molecular formula is equal to your empirical formula times a multiplication factor. How do you find that multiplication factor? Is relatively simple, and that's what this second equation is. You would take the molar mass of your compound, which is typically the larger number, and divide it by the molar mass of your empirical formula, which is typically the smaller number. And that's how you get your N. And finally, we're going to talk about electron dot structures or Lewis dot structures or electron dot diagrams. Those are all the same name. And that's basically telling us how many valence electrons there are for an element. And if you recall, I gave you 2 ways to draw an electron dot diagram. The first would be the ring around the rosy. So in ring around rosy, you'd have the element symbol. And let's say, for example, I had 5 valence electrons. I would start at the top and just put 1 in every corner until I have to start pairing up. Now the second acceptable version would be this, where you have S's at the top and then P's on every side. So if I were to fill in 4 valence electrons. So let's say my next element has 4 valence electrons. So element Y, it has 4. I would fill the top first and then go and fill on the next, because each side, this would represent the S and the other parts would represent the p orbitals. So I accept both versions. Both are correct in my class. So either way would be correct. Now we've done a complete review of empirical formulas and chemical compounds. The reason why I did a quick review on molecular formulas, empirical formulas, it's because this is what this unit focuses on. The chemical formulas. How do we come up with these simple ratios? And that's what we're going to do. But before we go ahead and do that, we have to talk about the types of bonds, the types of compounds that we are going to encounter. The first thing we need to define are, what are compounds? And compounds result when 2 or more atoms combine chemically through the formation of chemical bonds. Chemical bonds are basically attractive forces between atoms, and chemical bonds form in ways so that you can minimize their potential energy. So there are 3 major types of compounds that we're going to encounter. The first one are metallic compounds, the second are ionic compounds, and the third are covalent compounds. And so we're going to see the properties of each compound, and then we're going to finally talk about, in the next lecture, how to start naming these compounds and determining their chemical formulas based on the name. So metallic compounds. Metallic compounds are pretty much very unique because they have what are known as the sea of electrons, and those are mobile electrons that move within each within each metal element, and they create a metallic bond due to the attraction between the metal cation, so these metals right here, and these moving electrons. Since they're so mobile, it's such a high attractive force. Now, metallics are very tightly packed atoms and very good conductors of heat and electricity. And the reason why they're good conductors of heat and electricity are these sea of electrons, these mobile electrons. They're constantly moving, allowing the flow of electricity or heat to go through the metal. And these valence electrons, these sea of electrons are made of valence electrons being shared amongst the metal cations. And the reason why they constantly move is because they are loosely attracted to the atomic nucleus, because metal atoms are relatively large in size. Now, these mobile electrons are what causes the mobile charged particles and allowing, again, the flow of heat. And these are also known as delocalized electrons. And they're the reason why you have unique properties for metals, such as high conductivity and high melting points. So here are some of the properties. They're thermal conductive, so they conduct heat. They're electrical conductivity, so conduct electricity. They're malleable, ductile. So these are review from what we're rating you from the last unit. And alloys are special because alloys are a mixture of metal elements or elements that have metallic properties. And these are a list of very common alloys. Brass, bronze, dental amalgam, so this is the metallic filling that you have in your mouth if you have the metallic kind. Lead shots, pewter, stainless steel. Yes, steel is a combination of metallic elements. And sterling silver. Yes, sterling silver is not pure silver. It's a mixture of silver and another element. So we've talked about metallic bonds. Let's go ahead and talk about ionic bonds. Ionic bond is between a metal and a nonmetal. So if you think about the periodic table, there's always going to be one element on the left side of the periodic table and one on the right side of the periodic table. And when you form ionic bonds, one element is going to gain while the other one is going to lose. And based on the last unit, you should know that the metal is going to be the one that loses, while the nonmetal is the one that's going to gain. Now, because they both have a positive and a negative charge, they are going to have what is known as electrostatic attraction, because now you have a positive charge being attracted to the negative charge. And that is what causes ionic bonds to have such a strong bond. Now, ionic compounds are solid at room temperature. They form crystal structures. Again, they're made of a metal bonded to a nonmetal. And they can conduct heat and electricity only when it is in the aqueous stage. So that means you have to dissolve it in water, or when it's in the molten state. So you have to heat it up until it's liquefied. So it's in a liquid state. And you have to understand that ionic crystalline solids are very tightly packed. So here is the structure of sodium chloride, normal table salt. If you notice, it's so structured. You have a chlorine, 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 and the next row you'd have a sodium, 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 next row chlorine, 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 chlorine. They're tightly packed. And this right here, this type of pattern, they have names, and these are typically called what are lattices, and they form unit cells. And so basically a lattice is a repeating pattern within a solid crystalline ionic compound, and they give off a specific energy, and this energy is known as a lattice energy. It's the energy given off when two oppositely charged ions in the gaseous phase come together to form a solid. So as if I had a sodium gas and a chlorine gas and they come together, it's the energy they give off when they form. So again, here's a crystal structure. So this specific example is the crystal structure for sodium chloride. And if you look at this, they form what are known as cubes. Look, each element is in a corner. This is called a cube. This has a specific name, and there are many types of crystal structures or unit cells. And I'm going to go ahead and show you some, but you don't need to know them. Cubic, which is the one I just showed you for sodium chloride. In this example, you have all the elements in the corner of the cube, but there's also this one little element in the center, and this is called BCC, so body-centered cubic cell. And here's another one where it's face center, and then tetragonal where it's slightly skewed, orthorhombic systems, rhombohedral, and monoclinical and triclinical. And so these are just a few examples of the different unit cells. You do not need to memorize them. I just wanted to show you that there are different structures for different elements, and they all fall under one of these type of unit cells. Now, lattice energy, though, let's go ahead and talk about lattice energy. The more charged ions, the more energy is given off. And the more energy given off, that means the stronger the ionic bond. And this only works if we're going to compare two ionic compounds. And Q is a charged ion, and A, so charged ion 1, A, would be the first element, and B would be your second compound. So 1A, 2A, that means this was the first ion, this was the second ion of your first compound. This is the first ion, the second ion of your second compound. And again, you do not need to memorize the equation right here. You just need to know what a lattice energy is. But I am going to give you an example. So for example, if we were comparing magnesium oxide and sodium chloride, we know sodium chloride has a +1 for the sodium and -1 for the chlorine. Magnesium, right here, oxide, magnesium has a +2 and oxygen has -2. And if we look at this, it's 1/4. So the question we have is, which one will have a stronger ionic bond? It's the one that has a larger number, and that was magnesium oxide. So magnesium oxide will be our stronger ionic bond. And by how much? It's by 4 times. Now that we've talked about ionic bonds, let's go ahead and talk about covalent bonds. Covalent bonds occur only between nonmetals, and they form when you have atoms that share, neither of them gain or lose, they share electrons between them, and they can share 2 or more electrons between them. And instead of calling them compounds, we call them molecules. Covalent, anytime you have a compound that has a covalent bond, they're called molecules. And anytime you have ionic bonds, they're called compounds. So I just want to go ahead and tell you that that type of terminology and the correction of what we've been talking about the whole entire semester. But here's one. If I had 2 hydrogen atoms, when they come together, neither of them will gain or lose. They end up sharing the electrons, and it will evenly be distributed between the 2 of them. And covalent compounds, you already should know, they are solid, liquid, or gas at room temperature, and they form what are known as molecular units, so molecules. They're made of only nonmetals, so a nonmetal bonded to a nonmetal. Here are some examples of what are known as crystalline solids or covalent network crystalline solids. That means you have covalent bonds, and then they are very large and they have some type of repetitive structure. This right here on the left-hand side is what you have in your mechanical pencils. This is how your pencil works. Graphite works this way. They are sheets of carbon. Okay, each one of these dots are carbon bonded to another carbon, and they are layered on top of each other. And when you write on a sheet of paper, one of these layers are just removed. And so it just continues removing one layer until you have no more layers. And then your mechanical pencil is empty. This picture on the right is of a diamond. This is a very rigid structure of a diamond. They are compact, and if you notice, they are always, here's a central carbon, and then there are 4 bonded to it, and if we look at this, another 4, and if you take this, another 4. Carbons are very compact and very rigid and very strong. Now, there are 7 special covalent compounds you need to memorize. So this is something you need to memorize. These are known as diatomic molecules. The reason why they're known as diatomic molecules, in nature, you will never find a hydrogen atom. You will find hydrogen bonded to another hydrogen. You will never find nitrogen on its own. You will always find nitrogen bonded to a nitrogen. And oxygen will always be bonded to an oxygen. Fluorine, chlorine, bromine, and iodine. They will always bond to it themselves. And how you name them is basically just the single element. So example is hydrogen. Hydrogen is, H2 is hydrogen. So N2 is nitrogen, O2 is oxygen, F2 is fluorine, Cl2 is chlorine, Br2 is bromine, and I2 is iodine. But you have to understand, whenever I say iodine molecule, you have to think of I2 because then now I'm talking about the diatomic molecule. If I say an atom of iodine, then I would be talking about just one iodine. So to summarize everything we've learned in this quick video, the three types of chemical bonds that we've talked about are metallic, and those bonds are between only metals, and they are formed because of this sea of electrons, these mobile charged particles that are delocalized. And the second are ionic compounds, and these are formed between a cation and an anion, so between a metal and a non-metal. And finally, what we're going to talk about are the bonds between covalent bonds, where it's a sharing of electrons and it's only between non-metals. And I will see you guys tomorrow, and we will start talking about nomenclatures and naming compounds.